Okay, so very good afternoon, everybody. We're going to make a start. I realise people are still grabbing some lunch. My name's Sean Fitzgerald. I'm the Director of the Centre for Climate Repair. It is a real privilege to be able to host Professor Dan Schrag from Harvard University to share some thoughts today on the topic of the unknowability of solar geoengineering and actually why that matters. Now, I first met Dan in person in spring last year when I had the privilege of going and visiting Harvard University, who are now one of our partners of one of the projects that we are working on stratospheric aerosol injection. So one of Dan's colleagues, Frank Koich, we meet very regularly with, and we're sort of working on some aspects of that particular problem. But Dan's been thinking about this topic for rather longer than I have, and I've been doing this for 5 years, but Dan's been doing it for longer than that and certainly thinking about sorts of issues. And Harvard as a university is probably the best known university for the topic of solar radiation modification as a result of the presence of some other academics working with Dan in that arena. So we look forward very much to your thoughts, Dan, on this topic, and I know that you're going to inform and entertain us with your mind. So over to you.
Okay, can people hear me? Great. Okay, let's see if this works. So thank you all for coming. It's lovely to be here. I haven't actually been in this Cambridge for almost a decade, and so it's really nice to see old colleagues and friends and meet some new people. This is something, as Sean said, that I've been working on for a long time. I've been thinking about it for a long time. It's also a very controversial idea, and I want to talk about that. And I want to try to convince you that I actually think it's a really important topic to continue to think about, to continue to work on. There are lots of big questions that we don't understand. And as I'll show you, I think there's some questions we may never answer, and I'll show you why that's interesting. For those of you who haven't thought about this before, solar geoengineering or solar radiation management, the terms are interchangeable. It's the general idea of reflecting sunlight to cool the Earth and compensate for higher greenhouse gases. There are many different approaches to doing it, including space-based methods. There's actually a meeting going on right now in Nottingham on space-based technology for this. Until recently, I didn't take it seriously at all, and I still don't really. I have a dear friend from high school who is very involved in this, and he keeps trying to get me involved, and I keep thinking, you know, I have better things to do. And the reason is it's obscenely expensive. Probably trillions, maybe tens of trillions of dollars. And so I don't see this happening anytime soon. Stratospheric aerosols is the main topic. I am not going to talk about marine cloud brightening. If there's any use for marine cloud brightening at all, it's a local effect, and I'm not even sure it's a very good idea to do it. The time scale of it is too short for reasons I'll talk about in a minute. We're going to talk about stratospheric aerosol injection as the main aspect of this that matters. And let me just say, for people who don't have a background in understanding the circulation of the atmosphere, what we're talking about is injecting particles in the stratosphere. This is just a schematic of what the Brewer-Dobson circulation in the stratosphere looks like. This is the upper atmosphere above the troposphere. And what you see is there's basically two cells hemispherically semi-symmetric, where air rises at the equator and then subsides near the poles. So if you inject particles in this region here, they are transported towards the poles. And that's an important aspect of this that I'll come back to later. This is an old idea. This is a picture showing the eruption of Mount Pinatubo in the Philippines in the early 90s. So volcanoes do this. We know that, for example, Mount Tambora in Indonesia produced the year without summer in Europe. So we know that injection of sulfur into the stratosphere, which ultimately forms sulfate aerosols, can cool the climate. We know that this happens. Because Pinatubo was an equatorial injection, it actually spread on both hemispheres. Here is a picture showing the optical depth of the atmosphere. This is a picture in May of 91, April, May of 91, showing this is before the eruption of Pinatubo. This is right afterwards. You see that the particles spread very quickly. sulfur sulfate aerosols spread very quickly in the equatorial band east to west because of the circulation of the wind zonally is very quick. This is a few months after that, and you can see that the coverage is now all the way towards the poles, although there's still more of it at the tropics. And even several years later, there's still some residual, although it's dramatically reduced. Okay? The time scale of, we typically say it's the time scale of particles in the stratosphere is something like 6 months to maybe a couple of years. That time scale matters because partly it has to do with how much stuff you have to put in. We put a lot of sulfur in the troposphere from burning coal, from burning sulfur-rich fuels, and that actually causes acid rain. It causes a lot of air pollution and smog. It's a terrible thing. What we're talking about, because we're putting it in the stratosphere and the time scale is so much longer, we're talking about putting a tiny fraction of the amount of sulfur that we're loading into the troposphere. So people worry about the air pollution effects of this approach. By the way, you don't have to necessarily do this with sulfur. People are looking at other chemicals, including calcium carbonate, things that are much more benign. But sulfur is kind of the standard because that's what volcanoes do. Essentially, what we're talking about is engineering the Earth, doing an artificial volcano, doing injections of sulfur into the stratosphere. In the US, there were scientific reports on this back in the Johnson administration in the 60s. So this is not something that's some crazy new idea. It's actually been discussed for a long time, but it's picked up a lot in recent years. In 2007, this is before my friend David Keith moved to Harvard. I was visiting him in Calgary, and he was at the University of Calgary, we had a conversation that ultimately led to this conference that he and I hosted at the American Academy of Arts and Sciences in Cambridge, Massachusetts in 2007. This was, I think, one of the very earliest conferences. This was following a very important paper in 2006 that was published saying we had to think about this idea and take it seriously. And these were the questions. This is literally the slide that I introduced the conference with in 2007. How do we do it? What does it do to the climate system? What might go wrong? Does it postpone the need to reduce emissions? And a maybe different point, but a very important one, will it postpone the reduction of emissions, of CO2 emissions? Who controls it? When should we start, if at all? And what do we need to know before we start? This seemed back then a pretty good list of questions. What's interesting is in the last almost 20 years, there's been a huge amount, just like an exponential increase, because this was taboo back then. 2007, we had about a third of the invitees. We had very prominent climate scientists, economists, many different people invited to this workshop, and about a third of them refused to go because they said it was inappropriate to even talk about the idea. So this has always been an idea that's been controversial. My friend Ray Pierre Humbert, I gave a version of this talk a few months ago at Oxford. I was in Oxford for a week, and I intended it because Ray is at Oxford. I intended it to be a sort of a discussion with Ray Pierre Humbert, who's a prominent climate scientist, atmospheric dynamicist, and an old friend of mine. We've published papers together. And it turned out, unfortunately, Ray was, because of the antiquated retirement requirements at Cambridge and Oxford, he actually is now half-time at MIT in Boston. And so he was in Cambridge, the other Cambridge, while I was at Oxford. So unfortunately, he wasn't there. But I did a lot of the talk responding to an article that he had written with Michael Mann attacking the idea of solar geoengineering, saying that it was terrible. In particular, here's a quote from it. While it is certainly true that reducing sunlight can cause cooling, it acts on a very different part of the climate system than carbon dioxide, and efforts to offset carbon dioxide-caused warming with sunlight reduction would yield a very different climate, perhaps one unlike any seen before in Earth history, with massive shifts in atmospheric circulation and rainfall patterns and possible worsening of droughts. So, horrible specter. And, you know, one of the things that I realized, so while David Keith, when we brought David to Harvard, this was one of the main things David worked on. And while he was at Harvard, I didn't work on it so much, I'm embarrassed to say. I kind of got interested in other things. I kind of felt like that was his thing and I was doing something else. And a few years ago, David moved to Chicago, where he's created a big effort in climate engineering, including carbon removal, a lot of the things that the center here works on. And after he left, I started getting interested in this again. which is unfortunate. I'm very fond of David, and he certainly had a big influence on my thinking. But what I want to share with you is some of these newer thoughts on how to think about this problem. And I do think there's a huge discomfort in this. This is a famous example of the trolley problem. You know, you ask people, well, you're standing at a train track, and there's a fork in the track, and you have a switch, and the train is heading towards a bunch of people on the track. And there's, in this case, 5, but you can make it 10 or 20. You could do strange versions of this where it's like a family member versus a nod, or you can do all sorts of variants of this that have been done. But in this simple case, the question is, do you pull the switch and kill 1 person versus 5 people? And most people, when you ask them this, are comfortable pulling the switch. They realize that killing 1 person is better than killing 5 people. What's interesting is there's a variant of this where instead of a switch, you're with a very large person on a bridge, and if you push the person to their death on the track, they will stop the train and kill and save the 5 people. And in this case, people don't do it. They say, no, I'm not going to kill the person in order to save 5. Now, you both understand that the distinction between these is very subtle, right? You're killing 1 person versus 5 in either way you do it. But somehow we have a bias against act of commission versus acts of omission. Well, you know, it's really not my fault. Somehow the act of pulling the switch is different than actually pushing somebody to their death, murder, right? Now, ethicists and philosophers have thought about this a lot. I'm not going to talk about this much, but I do think this is underlying all of our discussion of solar geoengineering. Somehow, solar geoengineering feels intentional, and it's an act of commission. Climate change feels like an act of omission because it's global, it's collective action, and maybe because we kind of don't intend it. It's just an artifact of using fossil fuels. I don't think that argument holds philosophically or ethically, by the way. I think climate change is just as intentional. Just because it's inconvenient to stop it, it's expensive, doesn't shield us from the fact that we're doing it. We're still using fossil fuels even though we know. And just because it's a collective action problem doesn't mean that we don't have responsibility for it. But there is this difference. Somehow people feel more responsible if we intentionally modify the climate, even though we are modifying the climate with climate change, with greenhouse gases. Anyway, I'll come back to this. I want to mention the napkin diagram because Professor Hugh Hunt the other day at the seminar in the afternoon mentioned this diagram in his introduction and has it on his business card. Is that right? I actually think Ray Pierre Humbert is not just Ray, who has a huge hatred of this idea, but I think we all in this community have a lot of ideological unconscious bias. That is, we are susceptible to, the climate community has its own way of thinking about these problems, and I think we let that ideology infect our scientific thinking about this. And I think this diagram is an example of that. I think this diagram can be very helpful, but I also think it miscommunicates the problem to the community, or maybe it does communicate what you want, but I think what it does is it communicates not just the science, but also a certain ideological position that I actually think we need to separate. And I will talk about that later. So I'm just going to give you a friendly hard time on this diagram. Yeah, sorry. Okay, let me just start with something really simple. Here's an example. I could have chosen a dozen others. This is from Doug McMartin paper with Ben Kravitz, but there's literally dozens and dozens of other papers that show this. This is just a scenario where you take a climate model. This is scaled to a 1 degree average warming, so this is per degree of warming. What you see on the left is the 1 degree of warming average. You see the land warms more than the ocean. We understand why that is. This is a 1 degree centigrade global average warming. And this is doing the same, but with solar geoengineering. This is a very simplistic calculation. This is one that uses a very simple sulfur injection. You can do much more sophisticated ones that I'll show you in a minute. But the point is that if you look at these 2 temperature regimes and ask which world do I want to live in, the one on the right is a lot better than the one on the left for all sorts of reasons. Okay? Dramatically lower cooling. By the way, the scale is different. The red here is 3 degrees. The red here is 0.6 degrees, just to make that really clear. This is a very subtle climate change. This is massive climate change. Yes?
Is that some sort of feasible amount of cooling?
Yes, absolutely. This is feasible in terms of how much sulfur you have to put in? Absolutely. So, and this is the precipitation minus evaporation, so it just looks at the global, which by the way, doesn't actually mean much because the average, global average, annual average P minus E is not actually what matters to people. What matters is much smaller timescales, how many floods, how many droughts, which are not measured in year, average over the year, it's measured in much shorter timescales. But let's just look at this none the same. The point is that the anomalies are smaller here. Here the scale is only half what this is, but still, it's much milder, okay? So there's no question. And by the way, this is the general result. And there are other examples. I'm just going to run through this very quickly. But here's a paper by Peter Irvine with David Keith, with Kerry Emanuel, who's a meteorologist at MIT who works on hurricanes, Gabe Vecchi at Princeton. And what they did is they put essentially a solar geoengineering climate model, and they imposed it on a very high resolution model that simulates tropical cyclones, and showed that, surprise, surprise, when you actually reduce the warming with solar geoengineering, you reduce the cyclones and the intensity, because cyclones are driven by sea surface temperatures. You reduce the temperature, you actually reduce the problem of cyclones. So it essentially, whether it's hurricanes or whether it's droughts or whether it's just about everything else, actually preventing the warming from happening actually prevents a lot of the adverse weather conditions from happening. Okay? So I was interested in this problem long ago. I had a graduate student named Kami Dagan who worked on this. And we were interested in the problem because I was interested in how it didn't work. And let me just explain how I thought about it before. Reflecting sunlight is reflecting shortwave radiation from the sun, cooling the climate. Greenhouse gases work very differently. Greenhouse gases work 24 hours a day. Whether it's nighttime or daytime, infrared radiation is leaving the Earth, and greenhouse gases essentially absorb some of that and redirect it back to the Earth, warming the surface. Reflecting sunlight only works during the day. So it should have a very different effect on the diurnal cycle. And you wouldn't think it would actually compensate very well. You'd think it would introduce all sorts of funny things. And yet it turns out when people model this, it actually works way better than I anticipated. I was shocked when we first looked at this carefully. It actually does a remarkably good job of compensating. Now, maybe this is a glass half full, half empty kind of issue, but I think the general result is that it works really well. I was interested in where does it break down? Where does the effect of reflecting sunlight not compensate for the CO2 in the atmosphere? Because to me, that was the interesting part of this. Where does this fail? And I thought maybe this was it. Katie had this very clever idea. As some of you know, the way plants are dependent on CO2 for photosynthesis, but it turns out they also play an important role in the hydrologic cycle through evapotranspiration. There are little holes in their leaves called stomata, and they open those stomata to allow CO2 to get into the leaf for photosynthesis. It's also, though, a way that water evaporates from the plant. And there's a trade-off. Plants want to close their stomata to keep the water in water-stressed areas, but they need to open it to let the CO2 in. And so there's some plants that actually have elaborate systems for taking in CO2 at night, and then during the day when it gets very hot, they close them up to prevent the water from escaping. So there's all sorts of evolutionary strategies for managing this. The interesting thing is, if you increase CO2 and then solar geoengineer, the plant sees higher carbon dioxide levels, and actually it means it doesn't need to open its stomata as much because there's more CO2 in the air. That means they have what's called higher water use efficiency. And that leads to reduced evapotranspiration. So we thought, okay, that's interesting. Maybe in a geoengineered climate, the plants would evapotranspire less and you'd actually dry out the rainforests because they're actually closing their stomata more. It turns out it's a real effect. So this was the basic idea. But it turns out, so the idea is that in a solar geoengineering scenario, the temperature is maintained relatively constant, but the plant senses the high CO2 and reduces its transpiration. And so this was a way that it actually didn't compensate it, a sort of an asymmetry. We hypothesized that it might cause the hydrologic cycle in a geoengineered world to differ significantly from the present day. It turned out it's a second-order effect. It's real, it happens, it's just a minor effect. So every time I've sort of looked at that, I've been surprised at how well this actually works. So this assertion that Ray Pierre Humbert said that this is going to be massive shifts in circulation and worsening of droughts, that actually, there's no indication that that's true. Every simulation that I've ever seen suggests that it compensates remarkably well. And I've looked hard. And I think that's interesting. I will say part of the problem here is that people are often tempted to compare a sort of solar geoengineered world with the current day. And that's a big mistake. We don't get to stay where we are today, right? That's not the choice we have. We have the choice of solar geoengineering the world as CO2 rises or not doing it as CO2 rises. What we don't get to do is keep today's climate. So the comparison of some future climate with solar geoengineering to today's world is the wrong comparison. And I think a lot of people make that mistake when they analyze these results. What I want to say briefly, though, and this is the title of the talk, although it's not, I'm going to talk about more than this. A lot of the science being done right now on solar geoengineering is done by climate modelers who run climate models and then try to inform policymakers and decision makers about this technology, this approach. I was at a conference in South Africa last May, a year ago, and many people were there saying, oh, well, we need better models, higher resolution models, so we can predict how rainfall is going to change in Africa, in Ghana, for example, or in South Africa if we do solar geoengineering. And that's, of course, that's what policymakers want to know. I would like to know how this affects my country. And what I realized is that a lot of these people running these climate models didn't realize that actually this aspect of climate is rigorously unknowable. At least for now. And I want to talk about that just for a few minutes of why it's unknowable and what that means in terms of governance, because I think there's an interesting relationship philosophically about this. There's a big project that was started by people at Rutgers and a variety of other universities around the world, which basically is a solar geoengineering model comparison project called GeoMIP. And essentially, they're comparing here, this is 6 different models, each showing 2 calculations. One is a solar geoengineering calculation where they actually simulate the injection of sulfur into the stratosphere. That's on the left of all of these. So each of these pairs is a different model. And on the left, that's the sulfur injection. And on the right, this is the solar calculation, where a lot of climate simulations, instead of actually simulating the transport of sulfur, which most climate models don't actually do, they actually just turn the sun down, right? Which is, by the way, a perfectly good way to study some aspects of solar geoengineering, but it's like perfectly evenly distributing it, which is not the real world. If you actually injected sulfur in the stratosphere, it would not be perfectly even. It would be spotty because of the circulation. And all sorts of other factors, including water vapor and clouds and all sorts of other things. And so, this is the difference between the left and the right is an important difference. This might be what you would get if you had space mirrors, a third of the way towards the sun, right? Whereas on the left, this is what you would get if you injected aerosols into the stratosphere. And what I want to point out here is that these 6 different models give wildly different results spatially. They give the same general result, which is that the average temperature is remarkably, and I'm not showing you the warming simulation without solar geoengineering because the whole thing would be red. But the point is, if you look at the regional aspects of this, they're all over the place. For example, here, this is this cooling spot in North America. Let's just look at the sulfur ones because those are the ones that are uneven. So we see cooling here, but you see warming in this one and a little bit of warming here and warming here. You don't even know which direction this is going to affect. By the way, turns out this isn't true of just solar geoengineering calculations. It's true of general climate change calculations too. Regional forecasts are terrible in CMIP6 models. If you look at the IPCC, they don't emphasize this because they don't want to tell you how bad this is. But it turns out that forecasts at sort of smaller spatial scales are just not very good. We don't have any skill at that. There are multiple reasons for this. One of the big reasons has to do with internal variability in the climate system. There's a lot of internal variability. That is, year-to-year variation in weather. The climate models don't simulate things like El Nino very well, which is the largest source of interannual variability. That's just a problem. It's a very big problem. Some people think resolution will solve this someday. I'm a little skeptical of that. There may also be an aspect of this that, like weather, that there are limits to weather forecasts over about a 2-week time scale. As Ed Lorenz showed, the system is chaotic, and small differences in initial conditions can diverge rapidly when you're out 2 weeks. With climate, we mostly think about it as a deterministic system where you can make long-term forecasts, but it turns out there may be some spatial scales and time scales which are still chaotic in that system. We don't know that rigorously, but it's an interesting question of, we actually have never been able to do regional climate forecasts very well at long time scales. And it's not clear that we'll ever be able to. This is a famous quote. It's hard to predict, especially the future. It was attributed to Niels Bohr. It's also attributed to the Yankee catcher Yogi Berra. It's a very insightful quote, I think. It is hard to make predictions of the future. But I just want to show you another example of this. This is a calculation that Doug McMartin did where he basically looked at if we actually did solar geoengineering in a serious way, stabilizing at a 1.5 degree target, how long would it take to detect the signal? That is, how could you really know that you were doing it? And it's actually kind of shocking. This is temperature, precipitation, P minus E, and this is the year. And so what you can see here is that for a lot of the parts of the world, it would take a long time before you could even detect it above the noise of the climate system. That's because of internal variability. There's so much variability that being able to say at any one place, oh, this was affected by solar geoengineering, is actually really hard. You might be able to detect it earlier in the global average, but at the regional scale, really difficult. And I think we need to remember that we're dealing with a noisy, highly variable system that we don't understand perfectly, and that has important implications for how we think about this problem. And I think that's a really important thing. I'll give you one other example of sort of a little experiment that we did a few years ago, the world did, and we actually don't know much about it. This is ship tracks around the world. Ships, until relatively recently, emitted a lot of sulfur because when we got rid of sulfur in diesel fuel, because it created lots of air pollution, we allowed refineries to put it into bunker fuel, which people use for ships, with the idea that most of that sulfur is out in the middle of the ocean, doesn't affect air pollution in the same way. But there were some problems. For example, cruise ships that go into Athens or Venice or whatever would create all sorts of smog problems in southern Europe. People didn't like that. And so there was a ban, the IMO 2020 regulation, where they essentially, in January 1st, 2020, mandated that the sulfur content in fuel oil on ships was dramatically reduced. So this is a solar geoengineering experiment, except it's the opposite. Instead of adding sulfur, we removed sulfur. And we removed it from the troposphere, not the stratosphere, but there was a lot of it going in. So this happened. We took sulfur out of the troposphere, and as a result, the world warmed. The best climate model analysis of this that I've seen, and a bunch of people have done this, it's a small warming. It's like between 0.05 and 0.1 degrees Celsius. So it's a small effect, but it happened in a short amount of time over the Atlantic, where most of the ship tracks are. So most of the ships are in the Atlantic, and in the North Atlantic, this was like a 0.3 degree effect. But outside of the Atlantic, you can't tell anything. It's all in the noise. So just do that thought experiment for a second. If we started solar geoengineering, say, to stabilize at current levels, so we're not just like cooling the Earth by 2 degrees, we're just keeping it from continued warming, it would be decades before you could actually know we're doing it, because there's so much internal variability in the system. This is a hard problem. Another way to say this is a paper that Peter Irvine and David Keith wrote, and I just want to, they did an analysis, and they basically asked, where do you see exacerbation in the hydrologic cycle in this climate model that might be bad? And by the way, it's interesting, it's all positive, it's all wetter, not drier. And they say only 1.3% of land area sees exacerbation of change in water availability, and regions that are exacerbated see wetting, not drying, which is interesting. So forget this idea of extreme droughts. That doesn't seem to be the case. By the way, here's the point though. They did this with one model. What I showed you before was if you did it with 6 other models, you get 6 other results. The same general point, something like 1 or 2% might experience an exacerbation of the hydrologic cycle, but it would be different places. That leads to an interesting situation. And my undergraduate degree was in geology, but also in political theory. To me, John Rawls is one of the great political theorists. He was a Harvard professor, by the way. This is from his book, A Theory of Justice, 1971. He wrote, "The principles of justice are chosen behind a veil of ignorance. This ensures that no one is advantaged or disadvantaged in the choice of principles by the outcome of natural chance or the contingency of social circumstances. Since all are similarly situated and no one is able to design principles to favor his particular condition, the principles of justice are the result of a fair agreement or bargain." This was a towering work in political philosophy. People still argue about this book today. I actually think there's an analogy here, which is what we're talking about with solar geoengineering. Because of this dynamics, both the internal variability and frankly the fact that models are not able to predict regional variability very well, that the unknowability of local and regional impacts suggests that, that essentially this is going to make agreement on solar geoengineering easier. Because a country, you may say, okay, there's a 98% chance that you're going to be benefited and maybe a 2% chance that you're going to get harmed, but you don't know whether you're in the 2% or not. So should you do it? If it's 98% benefit, I suspect most countries would say, yeah, do it. That's very different than if you actually knew, oh, my country's going to get hurt, so now you're going to have to pay me compensation. Figuring that stuff out could be a mess. And by the way, that doesn't mean, and I think I have another thing here, if it's deployed sometime in the future, that doesn't mean countries won't point the finger at the solar geoengineering system to blame them for a storm or a drought or a flood. But rigorously identifying that this wouldn't have happened anyway is almost impossible. Maybe 50 or 100 years later with perfect data you could do it, but in the moment it's almost impossible. And I actually think the limits on knowledge on this in the climate system is important for us to remember. However, I do want to put one big caveat on this unknowability point. There are some aspects of this that may be knowable because we don't do it very well. This is going to become, I predict, a growing tension in this field because different solar geoengineering schemes, if you did it in a suboptimal way, you could really screw things up. Unfortunately, some of those things are a lot cheaper than others. Some of the different engineering approaches are cheaper than others. And I'll just give you a simple example. This is a paper by Alice Wells and others. This is a UK paper, mostly. And they simulated basically 2 different strategies. They first did a tropical injection, 10 north and 10 south. That's kind of like the classic Pinatubo example. 18 to 20 kilometers altitude. And then they did a multi-latitude injection at 30 south, 15 north, and 30 north. Slightly higher elevation, 21.5 kilometers. I'll come back to why that matters later. And they used an algorithm that controlled not just surface temperature, but also the interhemispheric gradient and the equator to pole gradient. Okay, so they actually tried to stabilize these things. So they were injecting different amounts at different times to try to keep these things constant. The result is quite striking. So here, global mean temperature. So this is what the world would have done if you didn't do solar geoengineering. And here are these 2 scenarios. And you see they're pretty similar. They keep the global temperature pretty constant. And interhemispheric gradient also is pretty much the same between the 2. But if you look at equator to pole temperature difference, there's a huge difference here. The one that's just the equatorial injection, that's the blue. The equator to pole temperature gradient is basically the same as if you had warmed. That's partly because of the high latitude warming, which doesn't work very well. Whereas in the red, you're doing a much better job of minimizing that equator to pole temperature gradient. I'll show you those simulations here. So this is the one that is the tropical injection, and you see the massive warming at the poles that's still happening. So we have some mechanistic understanding for what that is. That's partly because of, well, in the wintertime, it's because of the polar vortex. But in the summertime, which probably matters most because it's reflecting sunlight, it actually has to do with the Arctic oscillation and a climate dynamical reason, feedback. But here on the right, you could see it's much reduced, this high latitude warming. And that's because they're actively injecting more at the high latitudes in the summer and the other latitude at the other summer. So they're actually trying to control this. So the point is, how we do this matters. And I'll come back to that. But it actually, I'm a little worried that countries might do this poorly because it's cheaper, and therefore some people would get hurt because of the choices of how it's done. And that's actually important. So let's come back to this napkin diagram. I want to talk a little bit about the moral hazard, and I'm going to use the napkin diagram to talk about this. I actually think this is a perfectly good way of explaining the basic concept of it. So here is business as usual emissions. This is what would happen in terms of climate impacts. This isn't carbon dioxide in the atmosphere. This is climate impacts. This is what would happen if you stabilized or removed CO2. So, I mean, if you reduced emissions, eventually you would stabilize the climate and you would continue to have impacts, but you wouldn't have additional increases in temperature. That would be getting to net zero. And if we were really aggressive, we might be able to take CO2 out of the atmosphere and reduce the CO2 overall. And solar geoengineering in this flavor just cuts off the top and allows us to avoid all the impacts associated with this, right? So essentially, it's keeping us from experiencing all of this impact. The problem I have, and we can talk about this maybe after the talk, is that this represents one possible future. And I think it's actually an almost impossible future. It's an unlikely future. And it's bringing a lot of ideology, saying, yeah, I would like to see CO2 removal. Unfortunately, I'd like to see CO2 removal, by the way. I've worked on CO2 removal. I actually wrote a paper about it 20 years ago. So it's something I've been working on for a long time. But I can't actually imagine a world where, for example, the US pays or Europe pays hundreds of billions of dollars a year to remove CO2 if China and Poland and Russia are still burning coal. It's a collective action problem, and I don't know how to get around that. Absent a global governance of some sort that is far from existing today, I don't see carbon removal ever scaling. I wish it were not true. I mean, I would love to see it happen. I just don't think it'll actually ever happen at scale. I'd love to be wrong about that. And so I actually think we need, as scientists, to evaluate these approaches and technologies independent of ideology. I think part of and let me generalize this. For 2 decades, and I've said this when I teach about this problem, about solar geoengineering, I use the analogy to anesthesia. You wouldn't want to have surgery without anesthesia. Solar geoengineering is the anesthesia. Removing CO2 is the surgery. But just doing the anesthesia and never doing the surgery would be a bad mistake. That's what I do when I talk about it to students. I'm beginning to wonder if that was wrong, if that's my own ideological bias, or maybe I'm being defensive because the climate community is so hostile to the idea of solar geoengineering, and I'm being slightly defensive about it. So what I want to do is ask a simple question that is almost heresy in the climate community, which is, what would happen if we deployed solar geoengineering and didn't eliminate fossil fuel consumption? I actually think it's important to ask that question. Well, there's some simple answers. First of all, one of the first things people say is, oh, ocean acidification, that would still happen. And that's correct, right? Whatever the climate does, higher CO2 is going to, and it's a transient problem, but it's a transient problem over centuries to millennia, which is that the surface ocean is going to be slightly acidified. And when we say acidified, just to be clear, atmospheric CO2, this is the Mauna Loa CO2 record, and this is ocean pH measured in Hawaii. And you can see pH dropping by not even 1/10 of a pH unit. It's a subtle effect, but it's an important one, especially if you're a coral. Now, I worked on corals for a decade in the early part of my career. So I used corals to reconstruct climate and spent time diving all over the world. I'll tell you, if corals had a vote, they'd vote for solar geoengineering. And the reason is, while as bad as ocean acidification is, warming is much worse. The bleaching that's killing coral reefs today is caused by warming, not by acidification. So I'm not saying they would have no impacts. I'm not saying acidification is good, although I will say we don't actually have any idea what acidification will do to marine fisheries. And I will tell you also that if we really cared about marine ecology, overfishing is probably 100 times worse for marine ecology than ocean acidification. If we really cared about marine ecology, we'd reduce our fishing. But we're not doing that. Okay, so let's move on from ocean acidification. I actually think solar geoengineering, unfortunately, is not going to stop long-term sea level rise. It may slow it, but it's not going to stop it, particularly in Antarctica. First of all, when we talk about solar geoengineering, many different people have different ideas of what we would do. I think what is unlikely is that we would cool the Earth back to pre-industrial levels. I don't know about here in this Cambridge, but in my Cambridge, winters are really cold today. But 100 years ago, they were much colder. Nobody wants to go back 100 years to climate of what 100 years ago it was. By the way, farmers all over the world are adapted to today's climate. If you cooled the climate by 1.5 degrees, there would be chaos all over the world. Food shortages, it would be a mess. So figuring out what I can imagine getting agreement to keep the world from warming more, but not cooling it dramatically. That would be very difficult. What that means, though, in terms of sea level rise, Greenland is melting today, every summer. Antarctica, we're losing the ice shelves at 1.5 degrees. So freezing at 1.5 degrees doesn't stop sea level rise. It just slows it down. That keeps it from getting worse. So we're going to have long-term sea level rise. I won't talk about this much, but essentially in Antarctica in particular, once you lose the ice shelves, it's gravity. It doesn't matter what the temperature is anymore. You're going to lose that ice. When the Thwaites Glacier is unleashed, it's essentially a gravitational problem, not a temperature-related problem. But I want to talk a little bit about what's called the moral hazard. And I know some of you have to go because some of you are teaching it too. But I'm going to try to do this quickly. This is another quote from Ray Pierre Humbert and Mike Mann's piece in The Guardian. He said, "Plan B framing is the worst possible justification for developing solar geoengineering technology. It is laden in moral hazard." They weren't the first ones to use this term. This is an old term. It comes from economics. But essentially, what the idea of the moral hazard is that, what is it? It refers to the idea that if we actually stabilized temperature and climate, kept it from warming, that essentially we'd keep burning fossil fuels because we don't care about climate change anymore. Okay, and the way it is sometimes persuaded, in this diagram, if we did solar geoengineering, we'd follow the business as usual emissions trajectory. That's the way people think about it. And that's certainly what Ray Pierre Humbert was talking about. And that just makes our long-term predicament worse. So how big is it? I want to ask that question. How big is the actual moral hazard of solar geoengineering? Let's actually think through this as scientists. First of all, there's a sort of behavioral question I'm not really going to address, which is, will solar geoengineering actually make people care less about climate change? There are behavioral studies of this. I'll just give you a few examples here. I'm not going to talk about them. The answer is, it's equivocal. But most of the studies suggest no, that actually, it might actually make people care more about climate change because they'd freak out that we're actually doing something as crazy as engineering the whole climate for the world. But let's assume that people do care less about climate change because we're not warming anymore. So we stop the warming. We're still using fossil fuels. How large is the impact? And so I'm going to ask this in a few different ways. First of all, what fraction of emissions reductions in the past few decades has been due to a concern for climate change? Simple question. Turns out if you look at the UK, Europe, or the US, in the early, most of the emissions reductions was due to switching from coal to gas. Had nothing to do with concern for climate. More recently, deployment of wind and solar is really interesting. I think one of the best examples is Germany, which started it in some ways with very high feed-in tariffs in the early 2000s as part of Energiewende. But the driving factors for Energiewende, and people have studied this carefully, if you look at the discussions in Parliament, if you look at the discussions of interviews of people in Germany, first of all, it was industrial policy. The hope was that you would build up German solar industry and they would sell all that PV to the world. They got crushed by the Chinese, but they didn't know that back then. Number two, energy security. They were very dependent on Russian gas. They still are. And they really didn't want to, as the war in Ukraine certainly showed. Three, Germans hated nuclear power. Absolutely hated it. If you actually look at mostly what Energiewende has done, they've substituted solar and wind for nuclear. Climate was a factor, but it was probably a distant fourth. If you look at Chinese investment in EVs, it's the same thing. Industrial policy, energy security, air pollution was also more important than climate. If you look at Chinese investment in PV manufacturing and deployment, China is an extraordinary deployer and manufacturer selling PV to the world. Again, industrial policy, energy security, coal and gas imports, dependent on coal imports with making them very uncomfortable, and air pollution. Climate was a factor, but a distant fourth. Okay? So what about the future? In the future, emissions reductions, I would argue, are going to be driven mostly by technological displacement and cost, particularly in the developing world. Here's a cartoon that I love to show. It's actually from Vanity Fair from 1861, and it shows the whales celebrating the discovery of oil in Pennsylvania. In my home state of Massachusetts, the dominant energy industry in 1800 was whaling. Hard to imagine? Now, the point is, by the way, this is wrong. The whales didn't actually have a ball. But what I mean is it's wrong because probably 20th century whaling vessels powered by petroleum killed more whales than 18th century vessels powered by sails. So the oil wasn't actually good for the whales, but that's a separate discussion. The point is we didn't stop whaling in Massachusetts because we cared about the whales. Just to be clear, I care about the whales. But this isn't about that. Technological change happened because we discovered a technology that was better and cheaper, petroleum. And I think that's important. Let me just make one more point and then I'll wrap up. One of the big effects on the moral hazard is that solar geoengineering is going to change the way carbon is taken up. As I think most of you know, about half of the CO2 we emit to the atmosphere from fossil fuels is actually removed by the ocean and some by the land. On the ocean, because of reasons that we understand a little bit, and this is an example from the IPCC from back in like 2001, but this shows ocean models with the effect of CO2 rising only, and this includes the effect of temperature. And what you can see is that the ocean uptake, this plateau that happens as CO2 builds and the climate warms, that essentially, if you add the temperature effects, that it actually stratifies the ocean and reduces ocean uptake. That's pretty well understood, meaning solar geoengineering increases carbon uptake by the oceans. You have to include that in the moral hazard calculation. On land, it's an even bigger effect. This is on the left, terrestrial models with CO2 only rising, and this is with the temperature effects. Essentially, what's going on here is that respiration in soils is dramatically higher if warmer temperatures are warmer. And so if you stabilize the climate, you don't have as much of that. But the big effect here, and this could probably swallow up all the others, has to do with Siberian carbon and permafrost. By stabilizing the climate, you don't thaw the permafrost. There is something like 500 billion tons of carbon, not CO2, carbon, in frozen soils in the Arctic, most of it in Siberia for geological history reasons. If you reduce the warming in the coming centuries, you will reduce the release of carbon. Yeah. This could be bigger than everything else. Hundreds of gigatons of impact of carbon. So overall deployment of solar geoengineering, if it did reduce public pressure to decarbonize, would have a relatively minor effect on emissions, both past and future, based on both past and future. But because of the impacts on the carbon cycle, it could actually be negative. That is, solar geoengineering could ultimately result in lower CO2 in the atmosphere than if you didn't do it. I think people need to understand that, point that out. I did a calculation just to show you how big this effect is. I'm going to do a calculation. I'm going to assume that we do solar geoengineering and it increases emissions 25% over what it otherwise would have been. I think that's way more than the real world. I think it actually might be negative. But let's assume that it increases emissions 25% above what it otherwise would have been. I want to show you what that looks like. This is IPCC scenarios. So we're going to look at the yellow and the red. The green is completely impossible. And I think the purple is impossible as well for other reasons. In this case, the purple's brown. But this is what happens in CO2 in the atmosphere. We're somewhere between the yellow and the red. The yellow stabilizes around 550 parts per million by the end of the century. The red up at around 850. And it causes, in terms of warming, this is a whole bunch of climate models with lots of uncertainty, but we're talking about a difference between 2 and maybe 3.5 degrees of warming from today. What I want to show you now is just this sort of 25% assumption. So here's the yellow and the red, assuming emissions are 25% higher than they otherwise would have been. It's a sizable effect, but if you actually look at it in CO2 in the atmosphere, it's pretty tiny. All right, this assumes, by the way, a constant airborne fraction for people who care about that, but I want to wrap up, so we're not going to do that. But when you actually convert this to potential temperature, and again, you wouldn't experience this temperature because you're solar geoengineering, but this asks what the temperature would have been. It's a tiny effect. And the reason it has to do with the logarithmic relationship between CO2 and climate. In the higher scenario, it's like 0.05 degrees, whereas in the lower scenario, it's like 0.3 degrees. But the warming here, this starts at 1. So in fact, it's like the difference between the low scenario would be between 2.7 degrees of warming and maybe 3 degrees of warming. It's a tiny effect. So what I would conclude is that if there is a moral hazard, it's a tiny effect. It's not, it's used often as the major reason why we shouldn't do this. And to me, that's just nonsense. That's not understanding how the climate system works, how the carbon cycle works, and how the energy system and politics works. Now, there is a good thing about termination shock. If we do this, make no mistake, we're doing it for a long time. You get addicted to it because if you stop doing it, the climate would warm very quickly. Quickly, but not instantly. Here's a nice simulation from a bunch of models showing the termination of CO2, of solar geoengineering after 50 years. And what you see is the warming happens over like 5 to 10 years. Meaning you could decide to, if you stopped, you could decide to do it again in the next couple of years if you didn't like the results. It's not like it would warm tomorrow. I think that's important. Okay, I'm seeing time is up. I was going to talk about the cost, but I'm not going to do that. So how do I feel about solar geoengineering? I'll now tell you what I think. I've been trying to be as analytical as possible, removing my own biases and ideology. I like this quote from Winston Churchill. It has been said that democracy is the worst form of government except all the others that have been tried. I think that's how I feel about solar geoengineering. I think climate engineering is probably a terrible, arrogant, inappropriate response to dealing with climate change, except for the alternative, which is to let climate change happen. And I believe it's likely that some world leader or group of world leaders will deploy some form of solar geoengineering this century, unless our ability to adapt to climate change is much better than I think. Just because I think the suffering is going to be too much. And I think it is our obligation as climate scholars to try to understand it as much as possible, including all of the ways it could fail or be done poorly, as that is going to influence decisions. But it's really important. We don't get to decide. We're not going to decide whether we use it or not. We might, if we're lucky, influence some decisions in the future. And I think we have a moral obligation to think about that. So I'll just stop there. I had some more things I wanted to say, but we're out of time. Thanks very much.
I am acutely aware that some people do need to leave. So please don't feel sheepish. If you need to leave to get back to school, Andrew and co, just feel free to do so. However, I do think that there may be a few questions.
Sure.
So, any questions from the room? I'm going to take the very back to start with. Do we have a microphone? Well, just because I think we are recording it. So
Thanks. In a sort of alternative, very unrealistic world where you had control of the world's resources and money, etc., how would you go about implementing this in sort of 4 or 5 steps?
That's a good question. And I'm really glad that I don't have that obligation. I'm glad I'm not the emperor of the world. I was at a panel with David Keith a few weeks ago in Houston, Texas, and he said he would start right now. I'm coming around to that view. I actually think it's reckless to let the climate warm. We're already at 1.5 degrees. And the time scale, the inertia in the climate system is so much that we're going to be at 2 in no time and 3 soon enough. You know, climate policy discussions, you know, Trump gets elected and suddenly the world changes the way it thinks about climate change. The climate system doesn't care. The climate system is steady and slow and has massive inertia, has timescales of centuries to decades, to many millennia, to tens of thousands of years. And so I think we're ill-prepared to deal with those long timescales. I think it's compelling. I'm glad I don't have to decide to do this. But I think it's compelling to say, you know, the world is no longer safe to let it continue to warm. And we probably should, for now, the safest thing we can do is keep temperatures from going higher. I'm not talking about cooling it. I'm talking about putting in a little bit and starting to do solar geoengineering to keep things from getting out of control. But I recognize how controversial that is and uncomfortable that makes people feel. But unfortunately, I spend a lot of my time thinking about energy technology and policy. And I think a lot of the climate community has been drinking Kool-Aid or just imagining futures that don't exist in terms of decarbonization timescales. I think it's going to be much harder to decarbonize our society than people imagine.
Yeah, cool. Next, Daniel. By the way, keep the questions short and we'll keep the answers short.
I'll try to keep the answers short too.
As many. Okay.
Thanks, Dan. One question now, I'll let people go, but one of the questions that I really have is that working in this in such a short period of time, I've noticed that stratospheric aerosol ejection gets a much harder time than other solar radiation management schemes. Why do you think that is? People feel a lot easier eutrophying the oceans, they feel a lot easier digging massive holes into the Antarctic, but stratospheric aerosol injection gets much more scrutiny than other solar radiation management schemes.
Well, I think there's a lot of obvious reasons for that. I think, by the way, it also should get a lot more attention. All of the other engineering schemes that you're talking about, first of all, I think it's a terrible mistake that geoengineering is applied to the carbon cycle, as if somehow what we're talking about here with solar radiation management and carbon engineering are the same thing or subcategories of the same thing. They're not. They have totally different timescales. If you're going to remove carbon from the atmosphere, it's the same timescale as reducing emissions. And it's really expensive. This is much cheaper, and it works almost instantly. So it's a totally different thing, and it shouldn't even be talked about in the same sentence. So having a center that does both, fine, if that's how donors want to support it, but they're not the same thing. They're completely different. So that's number one. If you want to say just within solar radiation management, what about cloud brightening and other things? I frankly never have taken cloud brightening seriously. First of all, I don't think it works. But second, it has a time scale of hours to days. And if you're talking about doing something for the whole planet, I think it's a terrible idea to have that kind of short a time scale. That is, if you're going to engineer a system, having some a time scale of 6 months to 2 years, I infinitely prefer relative to something that I have to keep doing every day or else it'll fall away. That's just too vulnerable. The final thing on that I would say is people say, well, it might be good for protecting the Great Barrier Reef, for example. You know what? If you start doing it at the scale of the whole Great Barrier Reef, I think it's a bad idea. That becomes regional and it creates climate problems for the rest of the world. I don't think you can do solar radiation management effectively locally.
Okay.
I just don't think you can.
Well,
Yeah, thanks for the talk. It was absolutely fascinating, really refreshing to hear some of the views you expressed. I think we've got a situation where some climate scientists are really so opposed to this idea that they even try and block research for it. And I think, kind of like you, for what it's worth, I kind of agree that a lot of it comes down to the sort of moral hazard question and this idea that it's going to delay decarbonisation. And you've spoken about how the moral hazard question is maybe overstated as a problem, and you've paid some reference to the difficulties of decarbonisation. You've also talked about the sort of heretical nature of some of these ideas, I think, in the sort of climate community. So I'm just wondering, what do you see as the best way forward for getting people, getting people to understand that the moral hazard question is not as serious as it is, and maybe getting people to accept that decarbonisation isn't just a question of adding solar panels and batteries getting cheaper, so everything's going to be okay. What's the best way of actually opening up this conversation so that the people who are most concerned about climate change from the climate community, climate scientists, are not going as far as blocking research into something which obviously is a potential tool for stopping extreme warming?
It's an excellent question. My perspective is this, that a lot of that antipathy, again, comes from this commission versus omission issue. People somehow find, and by the way, the environmental community in general doesn't like, when I used to work on carbon sequestration 25 years ago, there were a lot of people who didn't like the idea. They loved solar panels, but they didn't like carbon sequestration because it was somehow an engineering approach and they wanted something more natural. There's nothing natural about photovoltaics, but that's fine. By the way, I love photovoltaics. I'm not opposed to them in any way. I just think we have to approach everything that we need. Part of the issue, I think, is that a lot of people in the climate community are woefully ignorant about energy technology and policy. They don't understand the economics or the financing of energy around the world. They don't understand the scale, and they don't understand how difficult it is to actually decarbonize. Some of my dearest friends, including Ray Pierre-Humbert, I love Ray, but I say to Ray, well, okay, Ray, you don't like solar geoengineering. What do you propose? And he said, oh, we should reduce emissions. I think, oh, Ray, thank you. What a brilliant idea. I wish I'd thought of that. We should reduce emissions. That's the answer. But what if we don't? And in studying energy technology for the last 20 years, I'm convinced that we're not going to. That is, I want to. I'm working really hard to figure out all the ways that we could accelerate this, and I don't think we're going to. And at least I think we need to understand this because, again, we don't get to decide what the appropriate thing to do is. Some world leader 30 or 50 years from now will decide based on how much suffering people in their country are experiencing. And it's our obligation to understand this deeply. I think it would be morally irresponsible for us not to do that. And by the way, that's not just figuring out how to do this well. It also means how to figure out how not to do it, and also any of the side effects, because all of those things are going to affect the decisions about deployment. And that's just responsible science. But I think at its core, it has to do with people who, and by the way, world leaders are partly responsible for that. This country, you have a law saying you're going to be net zero by 2050. You're not going to be net zero by 2050. But if people, as recently as just a year or two ago, I'd talk to colleagues and they'd say, oh yeah, we're going to be net zero for sure. I'm like, no, you're not. Look at the trajectory. You're not going to be at net zero. You've done a great job. You've been a world leader in many ways, but you're not going to be at net zero. And by the way, the world is not going to meet its targets. China will not be at net zero in 2060. India will not be at net zero by 2070. So Paris is wonderful in terms of aspiration, but in terms of actually delivering, it's limited by economics and technology. And we're not talking about a few $100 billion here and there. We're talking, McKinsey estimated it would take $6 trillion extra a year for the world to spend on this to make this happen. That's not happening. People are not willing to do that. I wish they were.
but it's not happening. And therefore, we have to think about what happens if they don't.
Great. So I'm afraid it's now
Yeah.
time past. So we're going to draw to a close. Hopefully, Dan, will you be able to stay around for a few
Absolutely.
minutes?
Happy to
those of
talk
you-
to people.
Those of you who have additional questions, please do hang around. So, Dan, I want to thank you so much indeed for illuminating us with your thoughts, and in particular, it was just the very final slide that you had. But it really echoes with actually the Centre for Climate Repair. The obligation, right, to try and learn more and be more informed about this topic, and to agree with Dan. Our job, certainly here as academics, is not to make political decisions, but we do have an obligation, I believe, to support our politicians by providing an evidence base and learning more about these sorts of issues. And it reminds me a little bit, I don't want to sort of go back over old ground, but that role in COVID, where Boris would say we're following the science. Strictly speaking, although that's what he said, the scientists were there to inform. The government was there to make decisions on this. And that's how it works in the policy arena. And we need to do our very best job to equip them with the knowledge and about the issues. It's not just the scientific issues, it's the non-scientific issues which involve our social scientist colleagues as well. But ultimately, as academics, we are here to try and support those who have to make very challenging decisions. And Dan, I'm very grateful to you for being very clear about the challenges we've got outside of geoengineering, but the world that we live in, and therefore the context in which this needs to fit and be supportive. Dan, thank you so much.